Alright, so we have a very classical question, number of islands. I think one of the early videos of Tech Lead, he mentioned it's one of his favorite interview question to ask for candidates. Let's talk about this question. We have a 2D map, grid, matrix, list of list, vector of vector with 0 and 1s, and 1 is island, 0 is water. We need to count the number of islands. We can connect an island in horizontal or vertical ways if they are adjacent to each other to form islands, and the islands are surrounded by water. We can also assume that outside this grid, every location, everywhere is water. So, so for this example, we can just pad a whole ring of water zeros around this. We can clearly see there is just one island here. For the second example, we have one island with four locations, 4 cells, 4 nodes, and the one tiny little island in the middle here. Because in the 4 adjacent directions, locations, it's all water, and one last island here. So for this question, we can basically treat this as a graph question. We need to find the number of connected components, where the connectivity is defined by the edges between the different nodes is the whether they are adjacent to each other in this horizontal or vertical fashion. So that's pretty much it. We can do this by visiting every location. That's equivalent to try every node in the graph. And if it's an island, if it's a 1, we just start a traversal to find all the nodes, all the pieces of land on that island, and just mark them as visited so that we don't double count. And once we have done this for the island, we just increment the counter for number of island by 1, and we try every location. If it's visited or if it's 0 water, we just skip that. Otherwise, we land. It's gonna be our first time landing on a physical island. We're gonna start a tow and just mark everywhere, every piece of land we see along the way to be visited. After we've done that, we increment the counter by 1. So we can do this either by DFS or BFS. It's not super clear which one is going to be more efficient by at this point of time. Or if you don't like, if you wanna, we can also use union find to solve this question. But I think DFS or BFS would just do fine. Let's talk about the time and space complexity. For the time complexity, either DFS or BFS or union find is going to be m multiplied by n, equivalent to the number of nodes on this graph, number of cells in this matrix, because we have to at least examine every location at least once to just ensure that we don't miss anything. And so that's that's the time complexity. That's some constant multiplied by n multiplied by n. You can I guess you can work out that more specific, but the constant is going to be dropped in the big O notation. So it's n multiplied by n in terms of time. For space, I guess this grid is passed in by a reference. So if you modify these cell values in there, then the other functions, other method, the other piece of code down the line, if they want to access this grid, they're gonna see a modified version of that. That would not be ideal. So I want to use a if it's me in my code, I would want to use an extra space n multiplied by n, which is the equivalent to the size of this island, to keep track of which node I have visited, which node I haven't. So for my case, I would prefer the using a set to keep track of that. So it's order of n multiplied by n, to be exact. There are some a discussion on the I guess on the for this problem. If you can just after you visit it, every a piece of land, you just change that value to be 0, so that you don't have to use extra data structure to keep track of whether you have visited this location or not. That basically would would change the grid, so that other piece of code will, if they want to use it, they're going to be in trouble. Or you can say if it's passed by copy, then that physical copy consists of n multiplied by n in terms of space. So that's the space. If you just somehow think that you can actually override it and don't count that into the space complexity, then for union find, it's obvious it's n multiplied by n. You have to sort of like put a cluster tag on every node, on every piece of land. So so that's required for union find. For DFS, you're looking at how big the stack can grow. So a quick worst case scenario for DFS is going to be looking like let me try to draw it. It will be looking like a zigzag puzzle kind of situation, which would cause the DFS to, since it wants to go as far as possible before backtracking, you will end up taking grow the stack to be proportional to the number of nodes on this graph. And for BFS, it's not. It will be more difficult to construct an example, but I think with careful design, you can get something like maybe something look like this. I'm not entirely sure. Yeah, but it's just have a lot of little branches within this graph. You can have as little leaves as possible, so that the BFS algorithm will actually grow the queue to be proportional to the size of this grid. And some of the discussion on I think the solution post for this says the BFS will be to be minimum of m multiplied by m, to be the minimum between the height or length. I just don't think that's correct. And for my purposes, I don't want to actually physically sync all this island, so that I'm gonna use an m by m hash map, a hash set, so that's just predominant. For that's just not my lower bound for the space. It's gonna be m multiplied by n. Yeah, so with that analysis be away, let's actually very quickly code this thing up. It's quite standard traversal and memorize stuff using a counter, so it's not too interesting. We handle some edge case here. Yeah, because it doesn't mention anything like the input. So basically, we're gonna check all the for the DFS or BFS version. We're gonna check every location. So we're gonna have a double loop here. So the R and C pair indicates a location on the grid or identify a node in the graph. So what we need to do is, if we have visited this, we're gonna skip. So for that, we need a hash set. We need a set to keep track of the place we have visited. Otherwise, we will just start. Otherwise, we will see whether this location is the first. Is an island or not. If it's island, we will start a traversal. Otherwise, we will just skip it as well. We can start a tow and increment the number of island. Islands. Increment this. We're gonna write a traversal into a method called tow. So for this method, it's gonna be we can have a DAG, so we'll be a little bit flexible about the switching between DFS or BFS. In the beginning, we would just have we would just have the neighbors of this location. So we will have a function to help us to get the 4 adjacent cell and also filter out the out of boundary cases. Okay. So if we pop left from the deck, it will be BFS. Yeah, we can do this actually. So we start with the first step. We step on the island, and we will, based on the strategy, we'll try to either go visit all the neighbors before we step further, or we can go in one direction as far as possible before we hit the water and backtracking. And whenever we visit a new piece of land, we will just keep track of that, marking that we have visited it. And if that location is an island, we will just try to remind us that we need to visit go further around that area. So that's pretty much the tow. And here's the method to get the valid neighborhood locations. So for the next row value, next column value in row -1, column, row +1, column, row column -1, row column +1. If it's within the board, then it's fine. So this is the helper function to give us the direction to expand the toe, and that's pretty much it. Let me quickly check. This is deck. We're popping from a deck. Just quickly noted it here. Yeah, let's try submit this. It looks good to me. Some arrow here. Blocking myself actually. It's the camera. Cannot unpack non-iterable int object. What does that? Oh, okay. Let me try to run this through an example. Okay. Okay, it's working. So yeah, here you have the code for either BFS or DFS traversal to solve this question, and because I'm using this set here, it's going to be n multiplied by m for the space. But I argue that if you don't have this, and instead if you modify the grid values, whenever you visit a location, you just set the grid R and C to be 0, so that it's physically sinking the land into water. Then the deck depends on, no matter it's BFS or DFS, there are always the worst case design of the grid that can trap you, that can trap a number of nodes that are proportional to the whole grid size into the deck. So the worst case space complexity for either this is still going to be m multiplied by n. So that's just my take on that. Okay, so that's the question for today.